In this video, we'll consider ODEs that describe forced oscillations, and in the solution process, we'll use complex replacement and the exponential response formula. In the first part, we'll find the general solution to x double dot plus 8x equals cosine of omega t, and we'll just think about and answer why this is called an undamped forced ODE. In the second part, we'll find the general solution to x double dot plus 2x dot plus 4x equals cosine of 3t. Go ahead and pause the video to work through these problems on your own, and I'll be back in a moment. Welcome back. So for the first problem, our ODE is x double dot plus 8x equals cosine of omega t. There are two main steps in finding the general solution to a differential equation. Step 1 is to solve the associated homogeneous equation. Okay? For this equation, that would be x sub h double dot, and I'm writing x sub h just to denote that this is the homogeneous equation, plus 8 times x sub h equals 0. So to solve this, we write down the characteristic polynomial. Characteristic polynomial p of s is equal to s squared plus 8. And the roots of this polynomial are given by s equals plus or minus the square root of 8 times I. Because these roots are purely imaginary, we know that the solution will be sinusoid. So we have x sub h is going to be equal to c1 cosine square root of 8t plus c2 times sine square root of 8t, where c1 and c2 are arbitrary constants. Now note that I've written this in rectangular form. I could also write this in polar form, being x sub h equals to an amplitude times cosine of square root of 8t minus a phase shift. These are both different representations for the same solution, but for this video, I'm just going to choose to write this in the rectangular form. Okay? So step 2 in finding the general solution is to now find a particular solution to the inhomogeneous equation. To do this, we'll first use complex replacement. And note that cosine omega t is equal to the real part of e to the I omega t. Now we can write down the complexified ODE, which would be z double dot plus 8z equals e to the I omega t. Okay? When we find a particular solution to this equation, we'll then take the real part to get a particular solution to our equation involving x. So xp, which is the particular solution, is the real part of zp, where zp is a particular solution to this equation. So now we apply the exponential response formula, which says that z sub p is equal to 1 over the characteristic polynomial evaluated at I times the frequency, I omega, times the right-hand side, so times e to the I omega t. So our characteristic polynomial is up here, and if we substitute I omega, we get minus omega squared plus 8. So right here we have 1 over 8 minus omega squared e to the I omega t. Now, you might have noticed that the amplitude here depends on omega. When omega squared is near 8, this amplitude is huge because we're dividing by a very small number. If omega squared equals 8, then we're dividing by 0, and this just blows up. When that's the case, we're in the situation called resonance, where the input frequency is the same as the natural frequency of the problem. So just to be safe, we're going to solve this when omega squared is not equal to 8. So we'll write that up here. OK, so now, since we're going to extract the real part of z sub p, we're going to write e to the I omega t as a sum of sines and cosines. So we get 1 over 8 minus omega squared times cosine omega t plus I sine omega t. OK, so now x sub p is just the real part of this expression. So x sub p, our particular solution, is 1 over 8 minus omega squared times cosine omega t. OK, so this is the particular solution. Now, we actually could have gotten this solution a lot faster and maybe skipped a few steps if we had noticed that we could have used the sinusoidal response formula because we have no damping here. The sinusoidal response formula just says that the particular solution is equal to 1 over the characteristic polynomial evaluated at I times omega, which we have here, times the right-hand side of our original equation. We can use that technique when the ODE on the left-hand side only has even derivatives, because then our characteristic polynomial will only have even powers. And when you raise I to an even power, you'll either get 1 or minus 1. So we'll have a real amplitude, and then we can just multiply by the right-hand side. So if you notice that, it can make your computations more convenient, but if you're unsure, you can always go through this computation. OK, so now we can actually write down the general solution, which I'll write over here. So the general solution x is equal to the solution to the homogeneous equation plus the particular solution. So we get x sub h was c1 cosine square root of 8t plus c2 sine square root of 8t. And then we add x sub p, our particular solution, plus 1 over 8 minus omega squared times cosine omega t. So this is our general solution for number 1. And we actually could have answered this question right away. Why is this called an undamped forced ODE? It's called undamped because we don't have a damping term. In other words, we don't have a term that's proportional to x dot in our ODE. And it's forced because we have this non-zero input on the right-hand side. So now I'm going to erase that side of the board, and we're going to work through number 2. OK, so we just solved an undamped forced ODE. This is actually an equation for a forced harmonic oscillator. We found the general solution to be this expression. But remember that this was only for the case when omega squared is not equal to 8. Now we're going to find the general solution to x double dot plus 2x dot plus 4x equals cosine of 3t. This is still a forced ODE, but now we have a damping term here because we have a term that is proportional to x dot. So like I said, for number 2, we're going to find the general solution to x double dot plus 2x dot plus 4x equals cosine of 3t. Again, the first step in finding the general solution is to solve the associated homogeneous solution. So step 1, solve the associated homogeneous equation. And in this case, that's given by x sub h double dot plus 2 times x sub h dot plus 4x sub h equals 0. And again, I've just replaced x by x sub h so that we remember that we're solving the homogeneous equation. So now we're going to need the characteristic polynomial, which is given by p of s is equal to s squared plus 2s plus 4. This polynomial has roots at minus 2 plus or minus the square root of 4 minus 16 all over 2, which is equal to minus 1 plus or minus the square root of 3i. Since the roots of the characteristic polynomial now have a real and an imaginary part, the solution to the homogeneous equation is written as follows. It will be e to the minus t times c3 cosine square root of 3t plus c4 sine of square root of 3t, where c3 and c4 are arbitrary constants. So this is the solution to the associated homogeneous equation. And now, in step 2, we need to find a particular solution to the inhomogeneous equation. So we'll find a particular solution. To do this, we're going to use complex replacement. And note that our right-hand side, cosine of 3t, is the real part of e to the I3t. So then the complexified ODE can be written as z double dot plus 2z dot plus 4 equals e to the I3t. Now we're going to solve this equation and find a particular solution for z. Then we'll take its real part, which will give us a particular solution for this equation. So x sub p, our particular solution, is going to be equal to the real part of z sub p, where zp is a particular solution to this equation. To find z sub p, we're going to use the ERF. So that tells us that z sub p is equal to 1 over the characteristic polynomial evaluated at I times 3 multiplied by the right-hand side of this equation, so times I3 to the t. Okay? So now, if we substitute I3 into the characteristic polynomial, we'll get that this is equal to 1 over minus 5 plus 6i times e to the I3t. And we want to extract the real and imaginary parts from zp, so we're going to rationalize this complex fraction by multiplying by the complex conjugate of the denominator. So we get that this is equal to minus 5 minus 6i over 61 once you simplify. And we're also going to write e to the I3t as the sum of sines and cosines. So multiplied by cosine of 3t plus I times sine of 3t. Okay. Now, x sub p, our particular solution for this equation, is going to be the real part of this expression. So x sub p is the real part of z sub p, and that's given by 1 over 61 times minus 5 cosine of 3t and then minus 6i times I gives us a plus 6 sine of 3t. So this is the particular solution to the ODE. And now the general solution for number 2 is going to be the sum of these two expressions. So I'll write that over here. So x is equal to x sub h plus x sub p, which we're going to write down is e to the minus t times c3 cosine root 3t plus c4 sine of root 3t plus the particular solution that we just found. So plus 1 over 61 times minus 5 cosine of 3t plus 6 sine of 3t. Okay, so now this is the general solution to number 2. I just want to point out a couple things. This is the general solution for an undamped forced harmonic oscillator. And we can see that each of these terms is just a pure sinusoid, and their amplitudes do not decay over time. However, in this case, where we have a damping term, we note that our solution to the homogeneous equation actually decays to 0 as time goes to infinity. So we have a transient part of our equation, and this would be the steady state part of our solution. So in this video, we found the general solution to two different types of forced oscillations.